And I gonna, while Edson is there talking to Henrique, I'm gonna introduce you. Just a second. So it's a pleasure to have Professor Siddhartha here today with us to talk to us. Professor Siddhartha got his bachelor's in the University of Kolkata, then his master's and his PhD in 1998 and 2003 at the Indian Institute of Science in Bangalore, India. And then he did he had three postdoc positions, one at the University of Cologne, 2002 to 2006, one at well-known to Brazilians ICTP Center for Theoretical Physics in Trieste, 2006 to 2008, and a postdoc at Urbana-Champaign in University of Illinois from 2008 to 2010. From 2010 to 2019, he has been an assistant. He was an assistant professor at the Indian Institute of Science in Bangalore, in Kolkata. Sorry, and then Kolkata, and now he's currently an associate professor at the Indian Institute of Science in Kolkata. So, Professor Siddhartha, it's a pleasure to have you here today. Thank you very much for accepting the invitation, and the microphone is yours.
Thank you, George, for the invitation. It's a distinct pleasure to be able to reach out to friends and colleagues from halfway across the world. I'm in a very, very different time zone from you guys, and people are going to sleep out here right now, but I'm very much awake because this is a wonderful and unique opportunity for me to, interact and meet with people, colleagues and friends from so far away. I might as well get started with today's seminar. Is this visible, George?
It is. It is.
Great. Okay.
Perfect.
So George already introduced me, and what I'll be talking about today is essentially the story of the Mott metal-insulator transition in dynamical mean field theory, and I'll be trying to tell you about what we feel is lying behind the numerical method of self-consistency. If you're not aware of the technicalities of dynamical mean field theory, I'll first give you a lengthy introduction to that. But before I do that, let me thank my collaborators on this project. My student, Abhirup Mukherjee, a very talented young man who has done the bulk of this work, and my friends and collaborators, Professors Vidyadhiraja and Taraftar. Vidyadhiraja is in JNC in Bangalore, and Professor Taraftar is at the IIT Kharagpur. These two gentlemen have been, wonderful colleagues and friends through my journey in recent times, and we've had wonderful discussions and inputs in everything. I've learned a lot from them, so I offer my thanks to them. And of course, I should thank the people who funded my research, which includes the Science and Engineering Research Board, the Government of India, and my home institution, which is IISER Kolkata. IISER actually stands for the Indian Institute of Science, Education and Research. So our institute is distinct from the Indian Institute of Science in Bangalore. All right, so let me get started. Let me start with the broadest questions out there, which I will try to hopefully shed some light on, which is the fact that there are many materials, and in fact families of materials, all of which are believed to be strongly correlated. These include the cuprates, the manganites, ruthenites, cobaltates, the organic conductors, the heavy fermion materials, and so many others that show phase diagrams in temperature versus something else, and that something else could be the pressure or doping. And these phase diagrams are extremely complex. They're full of all kinds of exciting things, which include metallic phases, as well as phases in which the electrons are ordered. Either they could be charge ordered or spin ordered. And there are several exciting phase transitions that are seen in many of these phase diagrams. The obvious question is, to a condensed matter theorist like myself, what gives rise to so much complexity in these materials? To narrow down the focus a little more, if we are focusing on the issue of transitions between metallic and insulating phases, then these are transitions that arise from competing tendencies. The localization of electrons, which are typically due to strong local repulsions, and the tendency to delocalize, which comes due to hopping between atomic orbitals in such strongly correlated systems. Now, can the physics of these metal insulator transitions, can they be learned from some simple model Hamiltonians? And also, can we actually gain insight by taking a local perspective, by asking the questions, by looking at the physics of a single site on the lattice and how it talks to the rest of the lattice, or even maybe a small cluster on the lattice and how that talks to the rest? To continue, a very generic phase diagram is what I've shown here on the right. And while we, what this very generic phase diagram shows is that apart from the Fermi liquid phase and the ordered phase, which could, for instance, correspond to a Mott insulator, we have several features in such a universal phase diagram that come filled with exciting possibilities. One of those is the fact that the ordered Mott insulating phase could end at a zero temperature quantum critical point, and above that you could have a region which we call the quantum critical region, where we find signatures of a gapless metallic phase which looks very different from the standard paradigm of the Fermi liquid. Now, this is seen in many different material systems and typically happens when the Fermi liquid is also in some sense destroyed and the ordered phase emerges. So is all of this, is this pointing towards something universal as a mechanism? And the other intriguing possibility is that in several of these materials, these strongly correlated materials, this quantum critical point gets hidden or obscured because superconducting fluctuations often tend to condense from the critical quantum fluctuations that are there in these strange metals. Why is this? So these are some of the bigger questions I'd like to address. But let me focus on a slightly more specific aspect of all of this, which is the Mott metal insulator transition, which basically involves freezing or jamming electrons in a lattice simply by cranking up or increasing the strength of local repulsions. Now, the simplest possible way in which to see this is to consider the case of a half-filled square lattice problem. So basically consider one electron per lattice site and then start up hopping between the nearest neighbor lattice sites. So that will be the kinetic energy, and also start up a, let's say, a weak on-site Hubbard repulsion. Okay, which means that if there is any site in the system which is doubly occupied, then you pay a repulsive cost, potential energy cost. Now, as long as the Hubbard repulsion U is much smaller than the bandwidth related to the kinetic energy, which is characterized by this hopping T, then we expect to be in a metallic system. On the other hand, it's not hard to argue for the fact that if the Hubbard repulsion U is much greater than the bandwidth related to the hopping, then it will, any electron in this half-filled system will not want to hop, because then the cost for double occupancy is extremely high. So this is a jammed state, and we call it the Mott insulator. Typically, these Mott insulators in realistic materials tend to, appear alongside with some magnetic ordering like Néel antiferromagnetism, that could be driven by super exchange physics. However, there are some material systems that do not show any magnetic order in the charge ordered Mott insulating phase. And the general belief among theorists is that the Mott metal insulator transition may coincide with magnetic ordering, but magnetic ordering is not central to the physics of the Mott insulator. So in order to study this, the physics of the Mott insulator and the transition from a metal to this Mott insulator, roughly 30 years ago, several theorists came up with a method called dynamical mean field theory, which offers a local perspective of the Mott metal insulator transition. And the way that happens is that we map the physics of the full bulk problem onto what we call an auxiliary system, which is to take a completely local perspective where we say that imagine that you have a thermodynamically large bulk system, and we focus on some site somewhere within the system, and we call that an impurity, which is the system on which we will focus. And all the dynamics now will be with regards to the electrons hopping in and out of this single site, or it may not be a single site, it could even be a cluster of sites, but essentially from a limited number of sites onto, electrons could hop onto and out of it, into the rest of the system. So the rest of the system is what we call a bath. And so essentially we've reduced the full problem in all its glory onto a completely local perspective of either single site or cluster, and talking to the rest, which is treated as some kind of a bath. Now, this, for the specific example of a Hubbard model, essentially reduces to the study of a single impurity Anderson model that is coupled to a bath of correlated conduction electrons through the tunneling of single particles, what we call single particle electronic hybridization. Let me give you a very quick introduction to the single impurity Anderson model. This is basically a single site, and which we call an impurity, on which we have a Hubbard U repulsion, and the filling can be adjusted, it can be tuned. Let's, for instance, focus on the particle whole symmetric impurity level, and we connect this impurity level to electronic conduction bath through single electron hopping. Okay, that's what we call hybridization. Now, we also assume that the electronic density of states of this bath, especially the local electronic density of states of this bath, is very simple. Why? Because we assume that the bath is non-interacting and that this density of states is basically just flat in energy space. It's completely featureless. Okay. Under these circumstances, if we start with a very weak Hubbard U on this impurity site and assume that there are no electronic correlations within the bath, then at very weak U, we see that if we look at the spectral function, essentially the density of states, electronic density of states on the impurity site, then we see for very small U compared to the hopping bandwidth in the conduction bath. So if that is very small, then we find that we get a broad resonance in the impurity spectral function near zero energy, okay, zero frequency. And this is characteristic of a very good Fermi liquid. On the other hand, as we increase the U with respect to the hopping bandwidth in the conduction bath, we find that this broad Kondo peak sharpens up, and spectral weight is dynamically transferred from this Kondo resonance in the center towards two new features at high frequencies that are called the Hubbard sidebands. And the belief is that the physics of these sidebands is associated with the correlated atomic levels on this impurity, and typically the physics of holes and doubles on the being on the impurity side, whereas the Kondo resonance is essentially the physics of a singly occupied impurity site, and how that talks to the conduction path. Now, if you continue to tune the Hubbard U on the impurity further, then you sharpen up this Kondo resonance and make it extremely sharp. But unless you set U equal to infinity, you can never open up a gap in this system, which means that for any finite U, you always get a gapless Fermi liquid metal corresponding to this Kondo resonance. So this model essentially never shows you any gapped local moment state. This should be contrasted. So before I show you that, so this was a cartoon-like sketch that I had here of the impurity spectral function. A calculation shows you that the spectral function proceeds in exactly the same way. Here I've plotted several of these impurity spectral functions at different values of U to the hopping bandwidth in the conduction path, from 0 to some very large value at 12.73. And you can see that essentially the story that I told you a few minutes ago is replicated here. So this is a numerical demonstration of the same. However, all of this should be contrasted with what happens in dynamical mean field theory, because there it turns out that we no longer are discussing the case of a single impurity Anderson model that is talking to a non-interacting bath. Actually, the bath consists of correlated electrons. And the reason we know that is because the local electronic density of states of the conduction bath is, by the requirement of self-consistency, programmed to look exactly identical to the spectral function on the impurity side. So whatever you get on the impurity side, okay, is exactly what you'd get on the sides of the bath as well. Now, what this does is that it actually leads to a metal-insulator transition, because now in this system, if you actually increase the U on the impurity side, you actually go from a very good Fermi liquid to a point where the Kondo resonance is extremely sharp, okay? And then if you further continue the tuning the U, what you actually do is that you cause this central peak to disappear, and the Hubbard sidebands are formed, and these are the only things that are left. And the disappearance of the central peak is then reveals a gap in the spectral function. And by self-consistency, this gap also exists in the insulator, and in the rest of the conduction bath. And that's what we call a paramagnetic insulator. Now, what we've ended up with here is actually the physics of a single local moment, where this impurity has completely decoupled from the bath. There's no single particle hybridization left when we end up in this insulator. So that's what we call the insulating state. Now, what's important to remember is that this local moment is actually a mimic for the case when there is no magnetic ordering in the insulator. Now, because typically you very often find that the insulators that you find coming out of Mott, out of the Mott-like mechanism, does lead to some kind of a magnetic ordering, nail antiferromagnetic order in the ground state or something like that. But here in today's talk, we'll be focusing on the case of the paramagnetic insulator, which corresponds to simply a local moment. Now, in DMFT, to continue the story of DMFT, we are talking about a half-filled Hubbard model on the Bethe lattice. And we actually have a Bethe lattice actually corresponds to a graph in which every node is talking to a set of other nodes. Okay, and here this picture is something I've taken from a recent work by Andrew Mitchell's group, where they've shown a Bethe lattice in which every node is connected to 3 others. Now, actually, the dynamical mean field theory's description of the Mott metal insulator transition is known to become exact when you take the coordination number for this lattice to become infinity, which means that any node on this lattice will couple to an infinite number of other nodes. Under that circumstance, something amazing happens, which is that, first of all, you can see that on any such Bethe lattice, no non-trivial loops can be formed. Because if you start out from any point on this lattice and head out, and finally you try to come back, then you can see that the only way to go anywhere and come back is by retracing the path. Furthermore, it turns out, and this was established in the late 1980s and early 90s, that in the limit of an infinite coordination number, all such journeys are rendered completely independent of one another, and they all become identical to one another, in the following sense, that the single particle self-energy for any such, for the Green's function corresponding to any such trajectory turns out to be local, which means that the self-energy is now only a function of frequency and not wave vector anymore. There's no wave vector dependence left anymore. So what this essentially means is that we can treat all these trajectories as being completely independent of one another, and that's what we're trying to, that's what is being shown in this right-hand side cartoon-like stretch, where any trajectory heading out of any given node on this lattice can be thought of as being this node talking to its own bath. And the DMFT on the Hubbard for the Hubbard half-filled Hubbard model on this Bethe lattice with an infinite number of neighbors essentially corresponds to the fact that the physics of every impurity is as if it's associated with its own bath, and each of these baths somehow appear to be distinct from one another. That's what this locality of the self-energy appears to suggest. So to spell out the results of DMFT, because this will be important for what we see ahead as well, what is observed, and this I'm now showing you a plot from a very famous PRL in 1993, is that when the U is very small, the Hubbard U on this impurity site is very small compared to the hopping bandwidth, then you see this broad Kondo resonance, and as you increase the U, it sharpens up, and these Hubbard sidebands start to form. At some value of U by delta, you begin to see these, the central Kondo peak getting almost isolated from these Hubbard sidebands. And then as you continue to crank up the U by delta further, the central peak continues to sharpen, which basically means that more and more spectral weight is being stolen from this central peak and pushed into these Hubbard sidebands. And along the way, what we can see is that something like a preformed gap appears to be entering into the impurity spectral function. So as long as we have the central Kondo peak, we still have a metal. But however, this, the appearance of these near zeros in the impurity spectral function is as if there is some kind of a, preformed gap, or you can also think of this as an optical gap that exists between the low energy metal and the high energy states that are lying within these Hubbard sidebands. And this is, taken to be a signal of the coexistence of a metal and an insulator. Okay. Now, finally, this central peak actually continuously shrinks to zero. Its width continuously shrinks to zero, and then it disappears at some critical value of U by delta. This is called the Brinkman-Rice scenario for the for the Mott metal-insulator transition, and this preformed gap then becomes the true gap. So this preformed gap then smoothly merges into what is called the true gap of the system, and what we are now left with is the local moment insulating phase, and this is a paramagnetic. So the two important things to remember are that the place where this optical gap first begins to appear, this preformed gap first appears in the impurity spectral function. This appears to be what people have referred to in the literature as the Mott-Hubbard scenario for the metal-insulator transition, whereas the continuous disappearance of the central Kondo peak and the shrinking and then its disappearance, that's what people refer to as the Brinkman-Rice scenario. Now, when you take all of this from 0 temperature across to finite temperature, then the famous phase diagram that was obtained about 30 years ago shows that the physics at the U critical 1, which is where the optical gap first appears, the Mott-Hubbard scenario, and UC2 where the central Kondo resonance disappears. So this UC1 and UC2 at 0 temperatures actually extend to finite temperatures, and they are actually spinodal lines that enclose a first order coexistence region where the metal and insulating solutions both exist at finite temperature. And then these two spinodal lines actually coalesce at some finite temperature, at a finite temperature thermal critical point. And there's a dashed line in between, which I hope you can see, which actually corresponds to a true first order line, which leads up from 0 temperature and ends at this finite temperature thermal critical point. And above the finite temperature critical point, you have a crossover between the metal and the insulator, which means that here it's sort of hard to tell between what is metal and what is insulator. Whereas to the left, you have a Fermi liquid, and to the right, you have the paramagnetic insulator. Now, this red phase is what would typically arise at very low temperatures if we'd allowed for some additional physics to lead to magnetic ordering. However, for the rest of this seminar, we are actually going to just focus on, just the physics of the coexistence region, and we're going to ignore the possibility of any ordered phase. The questions are, how does the single impurity Anderson model change in order to accommodate this metal insulator transition and such a rich phase diagram? Essentially, what are the physical mechanisms that drive all the rich, things that are being seen here in this temperature versus U by bandwidth phase diagram? So before I move from here, since I've finished the introduction, I'd be happy to take any questions that you might have.
I have a question, Siddhartha, a very quick one. If you go back to the slide where you showed the BRL results by Zhang, yes, this one. Right. Are these peaks that form at the top and the bottom of the side? Yeah, these peaks here, mainly.
These are the Hubbard sidebands.
But there is a difference between the slides with U over delta 2 and U over delta 4. 2.7 and 3 have these peaks at the top. Is there any many body physics related to these peaks, or did anyone study that?
Right, yes. So there are some DMFT works that appear to show that there are some special states that sit at the edges of these Hubbard sidebands. Okay. And that's what gives rise to these resonances, these resonant features. However, let me add that the appearance of some of these features, seems to depend on what kind of impurity solver you are using to solve this self-consistent single impurity Anderson model. If you use iterative perturbation theory and CTQMC, you appear to see these. On the other hand, if you use NRG, then you don't necessarily see these so well.
Okay.
So depending on the methods you use, these features appear more clearly than some others. But yeah, I mean, so I don't really have much more insight to say on that. There are some works that have looked into this, and I can give you the reference maybe after the seminar is over.
Okay, thank you.
All right. So then should I continue?
Yes.
Okay. All right. So then broadly speaking, our goal is the following. We're looking at the Mott metal insulator transition in infinite dimensions for the half-filled Hubbard model. And the idea is that DMFT treats this as being the physics of a single site, okay, which is hybridized, which we call as the impurity, and it is hybridized to a bath, which basically corresponds to the round trip trajectories, if you wish, starting out from that site on the lattice and coming back to that lattice. And this is what results in this 3-peak impurity spectral function, and also self-consistently on the bath. Now, our goal will be to try, in some sense, reverse engineer these results, which is, we want to find an effective Hamiltonian description for the impurity self-energy and ask, what physics within the Hamiltonian actually gave rise to everything that you see in such impurity spectral functions. But the way we will do it is that we will do it without demanding any self-consistency explicitly. So we will try to figure out what is a minimal model for an impurity talking to a bath. So we'll start with some model where we have an impurity site and which will be talking to some, a bath, which we will put into a Wilson chain-like representation, a 1D representation. And we'll ask ourselves, what do we have to do in such a system such that we can reproduce all the results that were seen in in DMFT. Now, a similar approach was considered briefly by C and Kotliar for an extended Hubbard model in 1993, but it doesn't seem to have been followed up since then. So what we're going to do is that we'll take this single impurity Anderson model, the one that I showed you earlier, but we're going to extend it. What do I mean by extend it? What I mean is the following. We'll take an impurity site, an impurity which has the Hubbard U, repulsion U on it, and we will treat its coupling to a conduction bath, which we've given a Wilson chain-like mapping. So it's a 1D mapping, okay, for the conduction bath. And I will, for the rest of the seminar, I will consider the site that talks directly to the impurity as being the 0th site of the bath. Some other people call it the first site. I will be referring to it as the 0th site. Okay. Then the next site I'll call the first site, and so on and so forth. Now, of course, there's a hopping that connects all these sites to one another in the conduction bath. But the 0th site of the conduction bath talks to the impurity site via 2 couplings. Now, in the single impurity Anderson model that I told you about earlier, we would have had only this single particle hybridization between these 2 sites. But now I'm going to extend it by adding also a Kondo spin exchange explicitly between this impurity site and the bath 0th site. And I'm going to do one more thing. I'm going to put in a Hubbard on-site correlation on the 0th site of the bath. And for starters, I'm going to keep the sign of this Hubbard correlation very general, which means that it could be repulsive or it could be attractive. And we will see by treating this model under renormalization group using a non-perturbative renormalization group method that we have developed recently called the unitary RG, we will see what this correlation on the 0th site of the conduction bath does to this problem. Is this clear, or should I spend a little more time clarifying?
No, that's fine. That's fine. Thank you.
Yeah. So then let me show you some of the results we obtained from our analysis.
In reality, just one question, Siddhartha.
Sure.
Are these hoppings, are they uniform?
Yes. So we will take all these T's to be uniform. So this is not a true Wilson chain that we obtain from NRG. Okay. This we will take to be a cartoon for a Wilson chain, where we've kept this to be, just a uniform hopping.
Okay. So I take back what I told you before we started. I think we can do that using insulating boson. Yeah.
Okay, great.
Okay.
Great.
Okay, yeah. Great. Thank you.
Yeah. So now let me show you some results I've got from here. And I'll show you these results first at a level where I hope which will be simple enough for even the graduate students attending this seminar to, to appreciate. And then if I have time, I will, for the sake of the experts, I will try and go into more details. So let me first show you the results at their simplest level, which is to show you what the phase diagram looks like, where I have plotted the phase diagram. So this is a 0 temperature solution of the problem, okay? Everything that I show you in this seminar will be 0 temperature unless I invoke temperature. So on the left-hand side, the phase diagram that I've shown here has the x-axis with the Kondo coupling, the bare value of the Kondo coupling, scaled by the hopping bandwidth in the conduction bath. And on the y-axis, I have this parameter R, which is basically the ratio of this, the minus of this UB, the Hubbard correlation on the zeroth side of the conduction bath, scaled by the Kondo coupling between the impurity site and the zeroth side. Okay, and what we will see is that at a critical value of this parameter R, the system is actually going to undergo a metal insulator transition, and that value will be 1/4, and we'll see where that comes from. Now, the other thing important to keep in mind is that I'm going to assume that this U bath is related to the U on the impurity side, the repulsive U, by a factor 1/10. Okay, and I'm going to invoke that the UB is opposite in sign to the on-site Hubbard on the impurity side, which means that if the impurity site has repulsion, I'm going to show you results here for an attractive interaction on the bath zeroth side. Now, what do these results look like? The phase diagram actually has several phases in it, so I'll take you through these phases one by one. The red phase here corresponds to a broad Kondo resonance, the red curve here, okay, on the impurity side, which basically means that we have a very weakly correlated local Fermi liquid in the system. This is because under renormalization group, the Kondo coupling and the single particle hybridization are both Rg relevant, whereas the on-site Hubbard repulsion on the impurity side is Rg irrelevant. Now the UB, the parameter UB, does not flow under renormalization group, and it is anyway very small in this red phase. Now in the blue phase, it turns out that the Kondo coupling is still relevant, but the single particle hybridization has become Rg irrelevant, which means that it has actually switched off in crossing the boundary between the red and the blue phases. Okay, and in the impurity spectral function, this actually the blue phase essentially corresponds to the physics where we have the Kondo resonance becoming isolated from the Hubbard sidebands, okay, which corresponds to a the value of this parameter R, which ranges almost from 0.76 times the critical value, okay, of the transition to all the way up to the transition. Now this blue phase is the new thing that we've discovered in some sense, because what we find here is that the only important players in the game are two parameters. One is the Kondo coupling between the impurity site and this zeroth site, which is, so in that sense, we are in the Kondo regime of the problem, which is what we expect from DMFT as well. And we also have the on-site attractive correlations on the conduction, zeroth side of the conduction bath. And what we will see is that this is what is responsible for the UC1 and the UC2, the passage into the coexistence region. This blue phase actually corresponds to the coexistence region that is seen in DMFT. And next, the purple region. The purple region actually corresponds to the local moment phase or the insulating paramagnetic phase of the system, where the impurity site has broken off from the conduction bath. So even the J becomes Rg relevant here. The V was already, the single particle hybridization was already Rg relevant. Now even the Kondo coupling becomes irrelevant. Instead, the Hubbard U on the impurity site, that becomes Rg relevant. So there has been a swap in the roles of what was irrelevant and what is relevant. Now this relevant Hubbard repulsion on the impurity site drives the gap between the two Hubbard sidebands. So this is the physics of the gapped out spectral function corresponding to the pink curve here. Finally, the black line corresponds to the metal insulator transition. And that is when this parameter is exactly equal to 1/4. And what we have is an extremely sharp central Kondo peak flanked by the two Hubbard sidebands. And that is the yellow, the green curve here. Now, in addition, the phase diagram also shows a gray region, which corresponds essentially to a non-interacting impurity site, which is completely decoupled from the conduction path. So essentially the U, J, and V, all these couplings are RG relevant here. So it's an extremely boring model out there. Now this model, it turns out that as we grow the size of the conduction path, we see that this gray region actually disappears. It shrinks within the phase diagram. So this is not a phase that is of any relevance in the thermodynamically large system. So the only physics that we need to worry about are the red phase, which is a good metal, the blue phase, which corresponds to a coexistence between the metal and insulating phases, and then the paramagnetic insulating phase, which is the purple phase, and the metal insulator transition, the true metal insulator transition, is on this black line.
Siddhartha, I have a question. You mentioned that when we grow the size of the Bethe, so this Bethe is finite. This chain is a finite chain.
So due to our our computation and the lack of computational resources, we have been working with only 5 Bethe sites. Okay. When we implement the problem, the RG as well as the numerical solutions of the impurity spectral functions and the phase diagram, we are only able to keep up to 5 Bethe sites because we actually do an exact diagonalization of the problem. Okay. So that's why this gray phase appears here. But what we've checked is that if we start from 2, 3, 4, and 5, and in some cases we've been able to go up to 6 Bethe sites, this gray region actually shrinks.
Okay. Edson has a question. Edson?
Yes, thank you, George. My question is, maybe I could leave it to the end of the talk, but I think it's important here, for at least for me, for my understanding.
Sure.
So now in these results you are showing here, as perhaps I admit, you fixed V, right?
Yes.
So when you have V and J,
we choose particular values of V, bare values, but under renormalization group, then something happens to them in different phases. So in the red phase, the V actually the V is RG relevant, but it switches off in the other phases.
Right. I was referring to the bare V.
Right. So the bare V, we always start with some small values of J, V, and U.
Okay. Very big. So yeah. So could I imagine in a situation in which V becomes large, or because actually here V and J, they kind of cooperate each other to form a single.
True.
Right.
True. So in some sense, you don't, when V and J truly cooperate, that's when both of them are RG relevant. The ground state is not just a Kondo singlet. It also has a charged triplet component in it, it turns out. I will show that very soon. So you also have holon-doublons on the impurity and zeroth sites.
So when you form a strong singlet, like a bounce or like a zero spin object, so then these should be decoupled from the rest of the system, right?
So what happens is the V switches off. So the strong Kondo singlet happens in the blue phase. So that's when all the single particle hybridization switches off, and in the ground state, you don't have any holon-doublon contributions left anymore. I will show you that very soon.
Okay, thank you.
Yeah, I'll show you some numerical plots, and then you can ask me again, Edson, if you haven't understood that.
Thank you.
Any other questions?
No.
Okay. So so let me just quickly show you how this phase diagram comes about under renormalization group. So this phase diagram, it turns out that the renormalization group equation for the Kondo coupling, for instance, looks like delta J, which is the update in the Kondo, Kondo coupling from one step to the next, goes as J, which is the Kondo coupling, into J plus 4UB. And this J plus 4UB part, you can see that it goes through a zero when UB hits a critical value, which is UB star is equal to minus J by 4. So at some particular attractive value of attractive interactions on this zeroth side of the conduction path, which is minus J by 4, that's actually this black line. That's where the Kondo coupling actually dies. But in order to spell that out more clearly, let me first start by telling you what were the RG flows, what do they look like in these different phases. So it turns out that when you're looking at the red phase, when you have a nice broad Kondo resonance, then both J and V are RG relevant and flow to strong coupling, which means that in this red phase, you never can stabilize the local moment. You always go to strong coupling and you have the Fermi liquid. Now, on the other hand, if you're in the blue phase and you try to go towards the, tune parameters to go towards the purple phase, then in that case, you find that this RG phase diagram actually is changed from the one at weak coupling in this thing, when J and V were small. Essentially what happens now is that there are some in the blue phase. If you're in the blue phase, then J and V again actually flow towards, can potentially flow towards strong coupling. Actually, let me correct myself. In the blue phase, only J flows towards strong coupling. V has switched off. However, if you tune UB, okay, across a particular value, which corresponds to 1/4, then the flows actually change and you can have flows towards the local moment. Now, these RG flows are what stabilize the purple phase, okay? And these are the flows that were missing out here, okay? So this is the RG flows that you would have expected for any single impurity Anderson model. But it turns out that once you put in this attractive correlations on the Bath zeroth side, then it turns out that this new phase, this intervening blue phase, is what changes the game. Because now you can actually have flows that you can see are actually separate. There is a separatrix that actually differentiates between the flows towards the Kondo coupling being strong and a Kondo coupling that just switches off and stabilizes the local moment. Now it turns out that exactly on this border between the red and blue phases, that's where the phase diagram for the single particle hybridization V looks qualitatively similar to what we have on the left out here, okay? So while this phase diagram is explicitly to show you what happens as you cross the black line, something similar is happening for the single particle hybridization also as you cross from the red phase into the blue one. To back up some of these RG flows in the phase diagram, we've computed some quantities that we can show you, and hopefully this will answer Edson's question. So what we've done here is that we've actually taken the ground state wave function and we've checked its overlap with either the spin singlet on the impurity and the zeroth side, the charge triplet on these two sides, which corresponds to a hole on the impurity side and a double on the zeroth side, plus the vice versa, or the local moments, which is basically you can have an upspin or a downspin on the impurity side and either holon or a doublon on the zeroth side. Now the red dots correspond to the overlaps of the ground state with the spin singlet. And as you can see, if we're coming from the metal towards the transition, which is at 1/4 of this parameter value, you can see that the the spin singlet content actually grows and goes to 1, which means that here in this initial region where R is less than roughly 0.12, you actually have both spin singlet as well as charge triplet content in the ground state, okay? Whereas as you come towards roughly 0.12, you can see that the spin singlet piece goes towards unity, and the holon-doublon content or the charge triplet content in the ground state is completely nullified and sent to 0. Exactly at the transition at 1/4, on the other hand, all spin singlet and charge triplet contents vanish, okay, all of a sudden, and instead the local moment overlap is seen to pick up, okay? So this is how the transition seems to happen. Does this answer your question, Edson?
Yeah, thank you.
Okay. So if we now also compute...
I have a question, Siddhartha.
Yes.
Why does it go to 1/2?
The local moments?
Okay. Yeah.
So I think this is going to 1/2 because I think we are taking the overlap of this with the two up spin states. So basically, it would have, if we would have done it with the other as well, we would have got 1/2.
Okay,
so okay. It's because of the double degeneracy.
Okay, thank you.
Now, on the other hand, I mean, we can also compute static correlations, spin and charge correlations in the ground state. And again, on this curve down here, we've actually, on this plot, we've shown 3 different kinds of correlations. One is the spin flip or the Kondo spin flip exchange fluctuations between the impurity and the Bethe zeroth site. Okay, that's the red one. And you can see that that actually picks up, okay, as you enter the Kondo phase. On the other hand, these are the charge isospins. So these are basically the holon-doublon fluctuations between the impurity and the D site. So that's the purple guy, okay? Between the impurity and the zeroth site, those actually decay, all right? So what we can see is that just like the overlaps, the spin flip and the charge flip correlations seem to go hand in hand with what we see with the overlaps between the spin singlet and the charge triplet, and that's not surprising. What is very interesting to see is that when the local moment phase is actually stabilized, it turns out that the blue crosses actually correspond to holon-doublon fluctuations between the Bethe zeroth site and the first site of the Bethe. Okay, so holon-doublon fluctuations actually kick off and start up in the conduction Bethe, and that's what seems to coincide with the local moment being stabilized. To explore this further, we actually have looked at quantities like mutual information. This is actually a way of seeing the entanglement between two sites. So it's called mutual information in the literature. And this actually is a quantitative measure of entanglement between the two sites. So if you look at the mutual information between the impurity site and the zeroth site, you can see that as you go through the good Fermi liquid metal into the Kondo regime, into the most strongly correlated Fermi liquid, and then it dies, you can see that the mutual information between the impurity and the impurity site and the Bethe zeroth site actually steadily decreases, plateaus out in the Kondo phase, and then dies as you get into the local moment phase. That's not surprising because the local moment is where the impurity site just gets cut off from the conduction Bethe. On the other hand, you can see that the mutual information between the zeroth site and the first site is completely, extremely small. Okay, in the it's almost zero out here, and then it becomes a very large value across the transition. So this seems to back up our intuition. But why is all of this happening? Well, this is happening because if you look very close to the transition, it turns out that holon-doublon fluctuations between the zeroth site and the first site are actually growing sharply in the metallic phase, very near the metal-insulator transition. It looked abrupt if you saw it on this scale, between 0 and 0.25. But when you plot it on a very sharp, a very small scale, close to the metal insulator transition, you actually see that it picks up and then appears to, abruptly jump and go to some value in the local moment or the insulating phase. So this appears to actually coincide with the, the formation of the Mott insulator. So essentially what we're indicating here is that some kind of pairing fluctuations are actually destabilizing the Kondo cloud and leading to the Mott phase forming. And that's a very important prediction that we're making. We can also explore further what happens if we are looking at the mutual information between the D site and the impurity site as we come very close to the transition. What seemed to be abrupt, it actually shows a gradual fall and then a sudden jump to 0. Similarly, the mutual information between the 0th site and the first site does not completely jump abruptly from 0 to whatever value in the insulating phase. There is a gradual rise and then there appears to be an abrupt jump. Similarly, if you look at the mutual information between the impurity site and the first site, which means you're actually looking for certain measure of longer ranged entanglement, you see that as you come towards the transition, it actually undergoes a non-monotonic growth. It grows, peaks, and then falls, okay, as you come to the local moment phase. And you can even ask, what about a tripartite entanglement? Suppose we measure the tripartite information, I3, between the impurity, 0, and first sites. You see that that also grows slightly as you come towards the transition and then falls to 0. So these are different ways, different results that we have that appear to indicate the, what is the physics behind this transition. Now, before I go any further, George, could you give me an indication of how much time I have left? Because I feel I've already taken about an hour.
It was a little bit less than an hour, so like 10-15 minutes.
Okay, so I have another 10-15 minutes?
Yes.
Okay, great. So then let me, so I hope that the graduate students would have been, on board at least till here. What I will show beyond here will hopefully satisfy the curiosity of the experts a little further, because we'll look somewhat closer at the transition now. Now, what is the minimal effective theory for this metal insulator transition? It is a model, essentially, that only has the Kondo coupling between the impurity site and the 0th site, and an attractive interaction on the bath 0th site. So, and of course, you have the kinetic energy in the conduction bath. So this is the simplified minimal effective theory for this transition. That's my claim. And the RG equation is what I'd shown you before, the RG equation for the Kondo coupling. So that's what dictates how you go from the blue phase into the purple phase. And that's what tells you how the Kondo peak actually disappears. Now, a lot of this physics can actually be learned by simplifying this model, okay, yet further by neglecting or switching off the hopping in the bath, and to just look at the physics of the two-site model, where we keep the Kondo coupling and this attractive interactions on the bath 0th side. And if this model can be solved exactly, and what it shows is something quite amazing. It shows that in this blue phase, the local moment phase, the local moment states, the doubly degenerate local moment states are already there in the spectrum at 0 eigenvalue. The Kondo singlet, however, is the true ground state on the metallic side. And as you come towards the transition, the Kondo singlet's energy is actually pushed up until it becomes degenerate exactly at the transition with the degenerate local moment states. And it is this level crossing physics that we claim is responsible for the Mott metal insulator transition at 0 temperature. So this is the simple way of looking at the quantum phase transition. Now,
could you remind me? Could you remind me what you showed? Could you remind me what is U tilde?
Oh, okay. UB tilde is essentially just another way of looking at the physics of this attractive correlations. So I've kept the tilde there, but don't worry about it. It's essentially just all intents and purposes, just the same as this attractive interactions on the zeroth side. And J tilde is just the same as this J.
Okay, thanks.
So my claim is that it's just this two-site model that can teach us a lot about this physics of this metal insulator transition. Now to go further, we can ask, can we see some notion of self-consistency within this model? After all, we solved this model using renormalization group, and computing spectral functions and et cetera, but we never appealed towards any self-consistency. But is there some hint of self-consistency in this model? And it turns out that there is. And the way to see that is to basically ask for the following. It turns out that that even within DMFT, the simplest way to look for self-consistency is to demand that an identical electronic density of states or spectral function is obtained at the impurity site and the zeroth site of the conduction path. This was what was invoked by Muller et al. In a PRL in 1995. Now here, what we do is we ask, what does the impurity spectral function look like on the zeroth site of the conduction path? And to obtain that, what we do is that we integrate out the impurity site altogether. The way we do that is to do a single shot integrating out of the zeroth site via the unitary renormalization group. However, for all intents and purposes, this integrating out is much like the Schreiber-Wolff transformation. And what that leads to is a new interaction on the zeroth site of the path, where the repulsion of the impurity has also now come on to the zeroth site. So now the effective interactions on the conduction zeroth side of the conduction path is the sum of the Hubbard repulsion, which was there on the impurity side, plus this attraction that we had there right from the beginning. And what you can see is that when we are in the phase, the strongly correlated Fermi liquid phase of the model, the sum of these two will always be repulsive. It will always lead to a repulsive on-site interaction on this conduction path. Okay, and then of course the connection between this zeroth site and the rest of the conduction path can be treated as the new effective single particle hybridization. So what this means essentially is that if we integrate out the impurity site, we can end up with a new effective single impurity Anderson model where we know that the impurity spectral function essentially goes through the same sequence of broad Kondo resonance to 3-peak spectral function to an extremely sharp spectral function as I increase the effective U on this path zeroth site. Okay, so what that means essentially is that if I'm in the metallic phase of the original model that we were studying, and if we are close to the metal insulator transition, then the physics that we would see on both on the impurity site as well as the bath zeroth site would look exactly like here. Okay, for all intents and purposes. So at least in the metallic phase, we expect an emergent self-consistency between the spectral functions of the impurity and the conduction bath zeroth site. Now, I would just like to spend a few minutes to quickly tell you about how our results actually tell you about the physics of coexistence at finite temperatures. Now, if you remember, I mentioned that at finite temperatures, we end up with a region in the phase diagram where we get a coexistence of the metal and insulating phases. Now, remember that the metallic solution is always the true ground state solution for all U less than UC2, as long as we're at 0 temperature. So strictly speaking, at 0 temperature, the true transition is only at UC2. And this involves a continuous sharpening of the Kondo peak, and which means that the Kondo scale should disappear at the transition, and the Landau quasi-particle residue for the Fermi liquid should also disappear. Now, the gap, therefore, will appear all of a sudden, the true gap appears all of a sudden at UC2 when the central peak disappears. Now, the insulating solution, however, is also known to exist at 0 temperature, because you could start from the local moment phase and adiabatically lower the U on the impurity side and enter into an insulating solution, even at 0 temperature. And that insulating solution, it turns out, is stable all the way up to UC1. And it is this peculiar thing that leads to the coexistence at finite temperatures. Now, how do we understand this from our 0 temperature solution? It turns out that if you look at the two-site effective minimal model, the JUB model, for the impurity site and the conduction bar 0th site, then UC1 is essentially where the two Hubbard sidebands get isolated for the first time as we enter into this JUB model. That point where this model becomes emergent, where the single particle hybridization switches off and all you're left with is the physics of the simplified model, that's what we'd call UC1. Okay, and what this means is that the spin singlet state is now very well stabilized, and you have a true Kondo, sharp Kondo resonance in the system. On the other hand, UC2 is where this the spin singlet ground state is pushed up by an increasing attractive interaction on the conduction bar 0th side until it goes and becomes degenerate with the local moment states. Okay, and it is at this degenerate point where you have a quantum phase transition, and the spectral function has an extremely sharp Kondo resonance of putatively 0 width. Okay, and this the Hubbard sidebands have, however, got flattened out. Okay, and you have this preformed gap which is separating out the Hubbard the sidebands from the central peak, and that's what we call the preformed gap. And that is the physics that has come into this spectral function, because the local moment states have also become true eigenstates in the problem. They're excited states, but they are eigenstates. And if we cross UC2, if we increase U beyond UC2, then of course the spin singlet state now is no longer the ground state. The local moment states become the ground state, and the Kondo peak then disappears. The U, on the other hand, becomes relevant, and you end up with a gapped impurity spectral function, and that is where the insulating state becomes truly the ground state. So what this means is that in terms of this JUB model and what we call the physics of UC1, the journey till UC2, where the metal-insulator transition happens and then going beyond, what this means is that if we take this quantum 0 temperature energy spectrum, and if we go to a thermal free energy at finite temperatures, then what we'd be saying is that if the free energy of the metal and the insulators, if they become equal, then of course you would get a double well like free energy potential. If you have a phase at finite temperature where the metal is less than the insulator, then of course you get an asymmetric double well, and vice versa when the insulator becomes the true ground state. Now, why would this happen? It would happen because the local moment states are degenerate, whereas the spin singlet state is unique. So therefore, the impurity, the contribution from the local moment states on the impurity side to the entropy, the thermal entropy, this will now make the insulating thermal free energy competitive with the metallic free energy at any finite temperature. Okay, so it's the degeneracy of these local moment excited states that leads to the coexistence at finite temperatures. Okay, so this is what leads to the finite temperature first order physics. Whereas, please remember, and I will repeat, that at 0 temperature, the only true transition is at UC2, okay, where this first order line actually ends. Okay, whereas the finite temperature thermal point, okay, the thermal phase transition is where the physics of UC1 and UC2 actually coalesce. So it's where the metal and insulator free energies become identical to their internal energies, or the quantum ground state energies. So essentially my claim is that the physics that we would see at UC2 will get repeated in some sense at this finite temperature critical point, because the spin singlet ground state and its physics will become degenerate with the physics of the local moment excited states, exactly there. So that's how the coexistence would come about at finite temperatures. Now, George, how much time do I have left? Because depending on that, I will either discuss just the last results or I will skip it and go to the conclusions.
A few minutes.
Okay, so in that case, let me just quickly summarize one other interesting result that we found, which is that in recent years, the practitioners of DMFT have shown that in the crossover region at finite temperatures lying above the finite temperature thermal critical point, you actually have the existence of quantum critical fluctuations. Okay, so this is very peculiar. So they've seen this via continuous time quantum Monte Carlo simulations as well as NRG simulations in DMFT. And different people, different groups have been suggesting that this coexistence region could therefore also actually have quantum fluctuations within it, and presumably because the physics at UC1 and UC2 have some kind of a quantum critical behavior. And we can actually see that. So we've actually got results which show how the metal insulator transition happens through the continuous disappearance of the Landau quasi-particle residue and the disappearance of the lifetime. So this is because the Kondo resonance actually vanishes as you approach UC2 at 0 temperature. And the quantum critical point simply comes from the degeneracy. This is what I'd said before. Now it turns out that we can show analytically that exactly when the degeneracy happens at 0 temperature, you do get the appearance of a non-Fermi liquid metal exactly there at the metal insulator transition. And if you look at various correlations, it turns out that apart from holon-doublon or pairing fluctuations between the 0th and 1st site, those kick up, okay, on the metallic side very close to the transitions, but you also see several other correlations picking up. For instance, if you look at the impurity site and the 1st and the 3rd sites, so if you look at the Kondo correlations between them, you see that those actually pick up as well on the metallic side as you approach the transition, as do holon-doublon fluctuations between the 0th site and the 1st and the 3rd sites. You can also ask what happens between the Kondo correlations between the impurity site and the 2nd and 4th bath sites. You see that even those pick up, as well as holon-doublon fluctuations between the 0th site and further into the bath. So what this is telling us is that a lot of spin fluctuations as well as pairing fluctuations become long-ranged in the metal as you approach the metal insulator transition. So this is how, this is a typical signature of critical, long-range correlations building up. And this is also seen through mutual informations. If you look at the mutual information between the impurity site and various sites on the conduction bath, starting from the 0th to all the way till the 4th, you see that they start picking up as you go towards the transition. So this would suggest that the coexistence region is actually, even though it shows hallmark of first order physics, there are actually critical fluctuations that ought to be there even within this coexistence region. And indeed, such fluctuations might actually be very difficult to see within this coexistence region simply because of the first order physics. However, in the region above TC, a lot of works by people like Dobrosavljevic and his group at Florida State, they've actually seen quantum critical fluctuations above TC, and also in some experimental signatures have been observed in some organic materials, okay, of this quantum critical region. So yeah, it would be interesting to actually look for these critical fluctuations directly within this coexistence region as well. So I'll go to my conclusions and outlook. Our goal was to actually look at an extended single impurity Anderson model, and without appealing to any self-consistency, to check whether we could, from such an effective model, capture some of the physics of DMFT. And indeed, my claim is that many of those have been understood from within the purview of such an effective model, impurity model. Now, what we see is that this impurity model needs the competition between Kondo screening physics as well as local attractive correlations in the bath. What this leads to is that you have an enhancement of pairing fluctuations in the bath adjacent to the impurity site, and that's what destroys the Kondo cloud, okay? And this provides an explanation for the coexistence of the Mott insulating and metallic phases at finite temperatures. It also tells us that there's a Mott criticality at 0 temperature, which involves a non-Fermi liquid like metal exactly at the transition, which which has long-range spin exchange and holon-doublon fluctuations in the bath. And the local moment Mott insulating phase transition actually appears at 0 temperature through a continuous transition, even though at finite temperature, it appears through first order physics. So in terms of outlook, I would like to now revisit some of those bigger questions. Do our findings actually appear to suggest some kind of a generic mechanism for a metal insulator transition leading to or away from Mott insulator physics? There are hints in our results that maybe this mechanism could be generic. Furthermore, what about doping? If we were to dope away from half filling, would the physics of this 0 temperature quantum critical point, would it show up? Would this first order coexistence physics be suppressed such that you could get a true quantum critical point at which some non-Fermi liquid physics would be revealed? And furthermore, we observed that there were critical pairing fluctuations in the conduction bath in the metallic side, very close to the transition. Could these fluctuations actually condense and lead to true superconductivity upon hole doping? Would all of this be some kind of an explanation maybe for the physics of the pseudo-gap phenomenon, where you actually see the coexistence of metallic physics, non-Fermi liquid metallic physics, and some kind of a gapped, putatively Mott insulating physics, which also shows a lot of fluctuations? Could all of this, what we've been seeing, could this be a hint at where this comes from? And could it be that even this infinite dimensional Hubbard model is giving us a suggestion of some intimate connection between the seemingly complex arrangement of phases in such phase diagrams? So with this as an outlook, I'd like to end and thank you.
Thank you very much, Siddhartha, for this very nice talk. So we are now open to questions. Enrique, you can open your microphone.
Are you listening now?
Yes.
Okay, fine. No, I would like to make two comments. I found your talk very, very interesting and exciting. I am afraid that I was not able to really follow all your explanations, but really it seems to be very, very exciting. I was wondering, you mentioned that is the Bethe lattice with an infinite neighborhood that could really map the problem into an Anderson impurity problem, correct?
Yes, yes.
Okay,
That's right.
so to what extent the Kondo peak that you obtain is going to be present in a real system?
Well,
this is my first question. The other one is just a very naive one, because yes, I studied the Mott transition in the Hubbard 3 approximation, the alloy analogy approximation. Is there any relationship that you can establish with that very, very initial and primitive approximation?
Okay, so let me take your questions one at a time. So first, thank you, Professor Anda, for your for your comments. So about whether the Kondo resonance can actually be seen in realistic systems. So the idea behind DMFT is, so let me go back straight to what DMFT would tell us, is that this central Kondo peak is essentially a way of seeing the Fermi liquid physics, because you are looking at a bulk metallic phase, but you're looking at it from a local viewpoint. So which means that the best thing that you can see locally would be the physics of a local Fermi liquid, which Nausius tells us is what it comes hand in hand with a strong spin singlet. On the other hand, if you were to carry out transport measurements, then the physics of this peak in this middle, the so-called Kondo resonance, that would correspond to a resistivity which presumably would go as T square in the bulk. So a bulk resistivity. So essentially, if you would trust what DMFT shows us about the mapping from a local perspective to a global bulk system, then this central peak is the thing that represents a good Fermi liquid metal with well-formed Landau quasi-particle excitations. So is that somewhat satisfactory?
Yes, sure. Thank you very much.
Okay. Right. Now, as far as the Hubbard 3 approximation is concerned, could you please remind me what the Hubbard 3 approximation was?
It is called the alloy analogy, and it is obtained from the equation of motion of the green function. You have the Hubbard 1 approximation that you decouple the green function at the first stage. If you go further, then there is a proposal of a decoupling procedure that is capable of describing the Mott transition, the Metal-Insulator transition.
So that's what people call the Mott-Hubbard scenario. Is that not true?
Sorry?
Is that what is popularly known in the literature as the Mott-Hubbard scenario, or a discontinuous first order transition? From what I remember, this is what John Hubbard found when he studied the Hubbard model. Is that not
exactly.
true?
Exactly.
Right. So essentially, in the Mott-Hubbard scenario, what Hubbard found, if I remember correctly, is that he did not find the central peak. He found
exactly. That's what I was remembering.
That's right. So essentially, what Hubbard found was that you have a sudden transition where the last thing, the two Hubbard sidebands appear discontinuously. So it's as if you jump from the upper picture, which you have, where you have a broad Kondo resonance, directly to this this two Hubbard sideband thing. So that is what we call the Mott-Hubbard scenario. On the other hand, when Brinkman and Rice studied the same transition, but by using a Gutzwiller variational wave function approach, what they found was that they found that this broad central peak actually sharpens up, and becomes the sharp Kondo resonance, and then its width continuously shrinks to 0 and then vanishes on the spot at a sudden value. So then Brinkman and Rice suggested that no, maybe the Mott-Insulator transition is a second order continuous transition. But funnily enough, they didn't see the physics of the Hubbard sidebands. So it's as if these two different approaches saw different things, but it was only DMFT in the early 90s that united these two and said, you know, actually you have both things happening at the same time.
Okay. Thank you very much.
Yeah, so if you have any further questions for Sanda, I'd be happy to take them.
No,
I mean,
for me, it's all right.
Okay.
Next, Edson, you have a question?
Yes, thank you, Professor Siddhartha, for a very nice talk. And I had a handful of questions, but many of those you have answered during your talk, especially the one when I had one of my questions was regarding the free energy, where you show nicely the two stable points, and in which and then probably you didn't mention, but probably this is responsible for the hysteresis.
That's right.
Behavior.
That's right.
All right.
Exactly.
But, okay.
Exactly.
But I think I have one question now. Is regarding maybe it's a little bit philosophical, and it's in regard to the Bethe lattice and your 1D toy model, and it was nice to see that you convinced that the Bethe lattice, you have just a trivial way. No, there's no non-trivial loop essentially. So you need to go and back and forth the same trajectory. So to
That's
speak.
right. That's right.
So this in your 1D, like 1G chain, like you call like maybe modified Wilson chain.
Yes.
When you also have the same trivial loop, right? So in this sense, you have the same simplicity of Bethe lattice.
Exactly.
So what would you expect in a realistic material where you have
right. So essentially, the idea. Okay, so this is the idea that the people people who created this method were pushing, is that if this transition, if DMFT is correct, then this Mott metal-insulator transition, at least in this artificial limit of the Bethe lattice in infinite dimensions, is driven by a self-energy Green's function, self-energy of the single particle Green's function that is purely local.
Yes.
And what that means is that the transition is also an impurity transition, which means essentially that I can see everything if I were to look completely locally at the system. So all I need to worry about is how particles leave any point in the system and how they come back. I don't really need to keep track of non-local intersite correlations between different sites of the bath, not even nearest neighbor. Okay, so that is what single site DMFT seem to be suggesting. Now, if you come down to let's say realistic lattices, let's say a two-dimensional square lattice, then of course the difficult question is, would this approximation work? Now it turns out that you actually have to improve this if you want to come down to lowered spatial dimensionality lattices, because then this neglecting the k dependence of the sigma of the single particle self energy may not necessarily be a good approximation, in the sense that the transition may not necessarily be a local one. So this may not be what Chi-Miao-Hsi has popularized in the form of local quantum criticality. The Mott metal-insulator transition might have non-local features, which come about by taking account of intersite correlations, in the lattice, which are being completely thrown away, in this artificial problem that was being studied. Now, if that is the case, then you can systematically improve DMFT by treating how a cluster talks to a bath. So instead of having just a single impurity, you could take a 2-impurity cluster or a 3 or a 4-impurity cluster, depending on the geometry of the lattice that you want to study. And in that sense, you would, this is what is called the Bethe-Pyle's improvement of the single site mean field theory. So did that answer your question to some extent?
Yeah, thank you.
Yeah, but I must also add that people have used single-site DMFT to death for studying a huge variety of systems and problems. And the claim is that there is something universal about these results. Not every aspect of that phase diagram will be universal, but the broad features may well be. And the hope is that if we have what is called a maximally frustrated Hubbard model, that is, if we were to study a Hubbard model in which, because of lattice geometries or whatever have you, all magnetic order can be frustrated such that you have something like a spin liquid, Mott insulator, then in that case, the belief is that this so-called toy model on this infinite dimensional Bethe lattice might actually contain the kernel of the important physics. That's the belief.
Okay, thank you.
Thank you, Edson. That was a wonderful question.
Siddhartha, I have a question. So maybe
yes.
I am jumping ahead a little bit here, but you suggested that we here in Brazil could do this calculation similar to the calculation that we did for the single impurity Anderson model, but just making it a little bit more complicated by adding this attractive new site. And as you did this calculation for using the unitary RG, I don't know. I know very little about your method, but I understand that the idea would be to reproduce what we did with the Kondo cloud, using slave boson and the equation of motion, and then just adding this attractive U site, and then looking at redoing what we did. So that's your idea.
Right. So essentially, the motivation would be that you would be tracking the passage through this phase diagram, okay, as you go from the blue phase into the purple phase. That is from the Kondo regime of this model, crossing the transition where the Kondo cloud dies, and to get into the local moment phase. Because in your earlier works, you've studied the Kondo cloud, but you've never seen its death.
Yeah, because we didn't want it to die, right?
That's right.
Yeah,
that's right.
Yeah.
But now the point is that if you are looking at using a model like a Kondo model as an input for DMFT, basically DMFT has an impurity model at its heart, then the Kondo cloud, when it exists, that is where you have the metal. But on the other hand, when the Kondo cloud dies, when it disappears, that's where you have the insulator. And the transition is where the Kondo cloud is just about to die. So you have a breakdown. It's not a complete breakdown, but you have a partial breakdown. So that passage, could your approach actually track that passage? Because that passage, if it reproduces what is seen in DMFT, then presumably that would be it would be an insightful way of looking at what's happening within DMFT. That's what we are also doing, essentially.
Okay.
We are proposing, like you said, a few days ago when we met online, we've reverse engineered the problem.
Okay.
We don't do any self-consistency. We choose some effective impurity model by hand, which has some minimal correlations in the bath. So we choose just Hubbard correlations on the site that couples to the impurity, and we keep its sign very general and find that the RG phase diagram only changes if you have attractive interactions, because it's only pairing fluctuations that can kill the Kondo cloud. If you have repulsive fluctuations, they only reinforce the Kondo cloud. They make it stronger. That's what we find under renormalization.
Okay.
So what that taught us is that pairing is a very natural enemy of the Kondo physics. And since the Kondo physics likes and leads to the metal, the local Fermi liquid, then if we promote some holon-doublon fluctuations between the zeroth site of the conduction bath and further, and its next neighbor onto the conduction bath, the first site, then promoting those fluctuations in the metal very close to the transition, that's actually what kills the Kondo cloud, because the spin flip fluctuations come down and these pairing fluctuations pick up.
Okay.
And that's what leads to the local moment. So the really peculiar thing that we see is that the pairing fluctuations don't lead to a superconductor on the other side. They actually lead to the Mott insulator on the other side. But you need them to destroy the metal.
Okay.
So it's as if you need small amount of subdominant pairing fluctuations in the metal to actually destabilize the metal and precipitate the Mott insulator. That's the peculiar thing. So it's as if the superconductivity is very confined to the neighborhood of the transition. And if you think about it, this is what people have been saying is happening in so many different phase diagrams, right? You have some ordered phase, which could be a Mott phase, some charge ordered phase where the charge degrees of freedom are frozen out. On the other side of the phase transition, some quantum critical point, you have the good Fermi liquid. But exactly at the quantum critical point, above it, you have a quantum critical strange metal. And very near the neighborhood of the quantum critical strange metal, you have superconductivity. And that's kind of what we're seeing here. That you actually need small amount of pairing fluctuations to kill the Fermi liquid and to lead to the Mott insulator.
Okay.
Because if you don't have that guy, you'll never get the Mott insulator. That's what we're seeing.
Okay. Okay.
I mean, it's very peculiar, but that's what it is.
It's very, very interesting. As Professor Henrique Anda said, your talk was very exciting. We are very excited. We're gonna have a meeting right after your talk to start discussing that and see how we can progress.
Right.
And then obviously we're gonna have meetings with you to pick up the details and everything.
Sure. So yeah, I mean, in another, if we get another chance to meet at some point,
sure.
My student and I will be happy to take you in more detail through these, these results. We can show you, for instance, we've also seen what happens at UC1. So today I showed you what happens at UC2, but we can also show you the physics at UC1, and that's equally rich. Because that's the physics where the local moment states actually enter into the the spectrum, the many-body spectrum. They appear as true eigenstates, and that is how the first order physics actually arises, because their appearance of the local moment states is the Mott-Hubbard scenario that Professor Anda was talking about, whereas the disappearance of the Kondo peak at UC2 is the Brinkman-Rice scenario that Brinkman and Rice found from their analysis. And what DMFT finds, and what we are finding from our simple model, is that there is a reason for these two physics to happen at very different energy scales. And that's because of these small attractive interactions that are there on that zeroth site of the bath. So all of this physics can only happen if you start up those small attractive interactions on the zeroth site of the bath. If they are not there, you will not get any of this physics. We can show you that in detail. So
very nice.
This
and
is
you
in
said
some sense, reverse engineering.
What is surprising is that DMFT can capture that.
That's right. And DMFT captures it through the self-consistent approach.
It's still very surprising to me.
Well, the funny thing is that, Son, you're right. But if our approach is correct, and we've added essentially only one new ingredient into the impurity model, which is this UB, the physics of this attractive correlation. Because if you think about it, the Kondo coupling would always have been there, even in the single impurity Anderson model. I mean, if you do Schreiber-Wolf, it becomes manifest, right? So my point is that we've added only one new ingredient into the impurity model, which is this local attractive interactions on the zeroth site. Now, if our analysis is correct, and this is the minimal impurity model talking to a correlated path that explains the DMFT physics, then what DMFT does during the self-consistent loop is that it actually performs something like a search in model space until it finds this particular model. So it's like an optimization. What self-consistency does is like a, is like a gradient descent. And this actually, the DMFT community does tell you in some of their papers, they actually do tell you that what they do is actually a gradient descent of the finite temperature thermal free energy until they come to the particular right, in quotes, right impurity model. The headache is that DMFT does not give you a Hamiltonian. DMFT gives you an action where you only see the impurity site having the correlations, and all the correlations of the bath are fed into the fact that the local spectral function of the bath looks exactly like what you have on the impurity site. Which means if the impurity site has that three-peak structure because of correlations, then so does the bath. But what is the Hamiltonian of the bath that does this? DMFT will not tell you.
So you are proposing, yes, precisely that Hamiltonian, that effect Hamiltonian.
Exactly. We've reverse engineered that.
Right.
And given that we can see all the results of DMFT coming out from this, it seems to us that this ought to be the right minimal model, because we've only added one parameter on top of, the simple single impurity Anderson model. And my claim is that we've added it at the right place. If we were to add these correlations, these attractive correlations anywhere but that particular site, then you would not be able to kill the Kondo cloud. The Kondo cloud would be very strong. Because in our way of thinking, roughly speaking, the Kondo cloud essentially is between this impurity site and the zeroth site, roughly speaking. That's where it's strong. So you have to hurt it where it is strong, because if you don't, then you will never be able to kill this guy. I mean, the transition will not happen. To see the transition, you really have to destroy the Kondo cloud. So that's why I reached out to you guys and, thought of asking you, from your method, how would you kill the Kondo cloud?
That's a good question. We love the Kondo cloud, so but now we start to think about its death.
We try to protect the Kondo cloud.
Exactly.
I completely understand that. Because if you don't have the Kondo cloud physics, then how would you get the metal in the metal-insulator transition? But now the point is, if you never kill the cloud, you'll never get the insulator. So then what is the minimal model to kill this cloud? So my claim is that you could go after this in two ways. One is you take some minimal model like ours and study it using your slave boson plus equation of motion method. That could be one way of doing it. The other way could be that you could take the impurity model that comes out of DMFT. For instance, if you run the DMFT loop, whether it is with NRG as the impurity solver or any other impurity solver, you can take the final endpoint impurity model that comes out of it. And especially if NRG is the impurity solver, then you again have a Wilson chain-like mapping. Now you could again take that impurity model and do your kind of analysis on that, which means that you take this Wilson chain and compute what is the spectral function on various sites of the conduction bath. And if that again looks like what we are seeing, then this is very strong evidence that even in DMFT, this kind of model is coming about.
Okay.
Do you see my point?
Yeah, that's the second option. That is, I had thought about that in the beginning. I thought that that's what you were doing, that you were running the DMFT, getting the end result and then studying that. But
no, we are not.
Okay. I believe we can do that. It's going to be computationally more demanding, I think, but I think it can be done too. The one where we studied just the real space model, which is a chain with the uniform hoppings, that can be done basically without making many modifications in the code that we have right now. It's just adding a site that has the other is a possibility too. So we just have we have a friend who was watching here. It's a lady from Universidade Federal de Minas Gerais, Maria Carolina Edson. She was watching the seminar, but she had to leave probably to teach or something like that. She does DMFT. So we could collaborate with her, get the DMFT results, and then run our method.
Because you see the point is, if we do it using the slave boson and
you are attacking from both sides, yeah.
That's right. Because the first approach is like ours. It assumes that there is a attractive correlation on the, let's say, the zeroth site, and then sees what you get.
Okay.
But then you'd want to also check this, whether this is actually what comes out of DMFT. Because that would be like, what shall we say? In some sense, that would be like the smoking gun. Because if DMFT also shows you the same thing, then nobody can deny.
Okay. Yeah, I agree.
Because you see, and my claim is, and this is for all of you, my claim is that if this is the right model for infinite dimensions, then, and we will now have the insight into how this happens. Because DMFT in principle works like a charm, but it does not educate you. It does not educate you on how it happened. But now we could sort of reverse engineer the problem and say, we now have the model that does all of this. So now what my student and I, Abhirup, have done next, which is we're hoping to, get into next once we've finished this and communicated this manuscript, we've also done some calculations where we take a model like this, and we've come up with a method by which we restore translation invariance, but without getting into self-consistency. Because self-consistency restores translation invariance, but does it as in the form of a numerical black box. We don't know how it does it. But Abhirup and I have invented a method, by which we can analytically restore translation invariance on any given lattice. Essentially, it uses Bloch's theorem to do so. So, and we can show you how that works analytically. And that then says that we can replace DMFT altogether because we have the right model, the effective impurity model, and then we'll recreate the bulk lattice from scratch without doing any self-consistency.
Okay.
And this time we'll have analytic plus numerical clarity.
Okay. Very nice. So Henrique, any more questions? Henrique is still there. So we are meeting through Skype right now, Henrique. It's almost 4. So let's meet with Marco and Edson too. And we can.
I have a meeting at 4.
You have a meeting at 4. So okay.
Yeah,
so
I don't think I will be able to meet you at 4.
No. Okay.
Unfortunately not.
Okay. So I will send an email to the two of you plus Mark. Okay. We're gonna find another time. Maybe tomorrow. Maybe tomorrow.
Fine.
So Siddhartha, thank you very much again. It was very nice, very exciting, and I hope this will, as in the, I don't know if you watched the Casablanca, I hope this will be the beginning of a very nice friendship.
Oh, that's one of the famous lines.
Yeah, well, I think this will be the beginning of a nice friendship.
I sincerely hope so, because, you know, I think since neither of our, you know, circles comes from this DMFT community, we are potentially bringing a completely new point of view to this game.
Okay.
With very different strengths.
Okay.
And, you know, and there is always the chance that we can hopefully do something quite unique in all of this.
Okay.
Because, you know, we are coming in with a fresh pair of eyes, you know, on fresh viewpoints. And I think that could potentially lead to some extremely interesting possibilities. And this could be the beginning of that.
Okay, very nice, very nice.
Thank you very much, Siddhartha.
Thank you.
Thank you. Yeah, thank you. Thank you, Prasanna.
Thank you. I'm gonna write you an email asking for these slides.
Sure, sure. So would you like it in PowerPoint?
Could be PowerPoint. Yeah, no problem. No problem.
Okay.
Okay.
Great.
Thank you very much.
Bye-bye.
And have a good night.
Thank you. Thank you.
Bye.